Hello, everyone. So we are from Group 10. Out. Okay. We are from Group 10. Zero point zero. No problem. Yes, sir. Yes, sir. Yes, sir. Yes, sir. Okay. Okay. So our topics is an analytical design study of a 56-inch ceiling fan with the impact on blade designs. We are from Group 10. So next. Okay. So we are actually 8 people's team, leading by Fakir, Sheik, Zihad, and Momen, Shahriar, Joarder. And my contribution of this project is as a technician and design for manufacturing. So next. Okay. So let me explain the abstract of our project and our paper. This paper actually presents the analytical study of a design of 56-inch ceiling fan, focusing particularly on the impact of blade design because the design of the because fan efficiency and the airflow distributions of any ceiling fan mainly depends on the blade design. So it is actually we have utilizing the advanced computational fluid dynamics models. Our research explores various blade geometries and their effects on enhancing aerodynamic performance of the ceiling fans. So the study we have identifies optimal blade curvature and angles that maximize air circulations while minimizing the energy uses because at the time we have to maintain the energy consumptions lowest so that our design actually mainly focused on that aerodynamics designs and the findings we offer in significant insight for the development of energy efficient ceiling fans in residential and commercial settings. So, and providing a balance between environmental sustainability and user comfort. So, our projects is actually consist of 9 different semi-knockdown parts. The main parts is our blade. Second thing is rotor design, down rod, top canopy, bottom canopy, and the last one is blade damping washer. Next. Okay. So let me introduce our fans actually introductions. The ceiling fans are actually universal. We all have in our homes, and this is very our design is mostly our focus area is not only residential but also the commercial settings, serving as the essential feature for maintaining comfort and the airflow. However, despite their prevalences, there's often room for improvements of any design. Just for our design also, we are actually hoping for more efficiency and performance in the future. Our project actually focused on addressing the gap by undertaking an analytical design study aimed at optimizing the blade and motor design standard for 56-inch ceiling fan by leveraging advanced computational fluid dynamics models and design for manufacturing and assembly analysis. Our primary goal is to enhance airflow distributions and efficiency while minimizing our energy consumptions. Next. Okay. So the aim of our project is the primary aim is the blades and motors design to achieve better airflow performance by carefully analyzing and refining the blade geometry and motor specification. We seek to maximize air circulations while minimizing energy usage. The optimization process actually involves iteratively adjusting design parameters based on computational simulations. Ultimately, our research not only advances the state of ceiling fan technology but also aligns with broader effects to promote energy efficient solutions for everyday appliances. Okay, existing ceiling fan designs. Traditional ceiling fans design typically feature blades made from materials such as wood, plastic, and metals. Our blades may vary in shape, size, and angle, influencing the airflow patterns and efficiency of the fan. Additionally, Our motor design has evolved to include various types of motors, such as induction motor or brushless DC motor, each offering different performance and characteristics. Our next portions will be covered by my another team members, and thank you all.
Okay, thank you. ভয়েস কি শোনা যাচ্ছে? Here the existing ceiling fan. Now we'll discuss the existing ceiling fan model. What had been before, and we will discuss after the changes on here now. The length of the blade is taken with the respective amount of CFM required, and the area under which the fan placed, typically 200 to 400 square feet fan blade, and the blade length is 400 mm to 600 mm to provide CFM of 2000 to 8000. But for optimum design, we will consider the fan length of 483.17 mm, as if the length of the fan is increased more, more motor power is required, and thus more operating cost. Fan blade profile is a single thickness sheet metal profile with the leading and trailing edges. The leading edge first encourages the air, and the blade angle of the leading edge is 3 degree, and the trailing edge varies from 7 degree to optimum the airflow and produce a uniform horizontal air column. So the new design, before doing the new design on the blade, so what are the things that we need to consider? We are not focusing on the motor design or something like that. We are only focusing on the blade shape, the blade design here. So when optimizing the blade design, overall several factors must be considered, including this. One is blade shape. The blade shape of the influence the airflow, distribution, and the efficiency. Curved blades, for example, may produce a smooth airflow pattern compared to straight blade. And the second option is we consider that is blade size. The length and width of the blades affect the fan's ability to move the air effectively. Longer blades can typically generate higher airflow velocity. And the third one is blade angle. The angle at which the blades are pitched relative to the fan's rotation axis determines the amount of the airflow pushed or pulls by the fan. Optimizing this angle can maximize the airflow while minimizing the energy consumptions. So these are the three things we consider before designing the ceiling fan blade. So here you can see the new ceiling fan designs here, where our twisting angle is 9 degree, and the lift angle we have done 5 degree. The before the twisting angle was 7 degree in previous design, and the lift angle was only 3 degree. So here we have changes that thing. So based on by focusing on these aspects of blade, we aim to develop a ceiling fan that not only delivers the superior airflow performance but also operate with the enhanced energy efficiency, meeting the demands of the modern consumers while reducing the environmental impact. So overall, if we see the comparative analysis here, from the aesthetic and surface treatment, the new design we have done that emphasize the aesthetic improvement with an aluminum chrome finish, suggesting a premium product line compared to the old design. Precision in design, the new design includes a specific angle for the twist and lift, which are likely calculated to improve the fan's efficiency and quality of the airflow, which is a step beyond the old design that primarily focuses on the general blade dimension for adequate airflow. Number third one is the new design appears to focus significantly on the structural advancement as the dampers and the reverse, which are likely to intend to improve the durability and reduce the noise also. So which are explicitly mentioned in our old design. We have done it before. So we will show later the some test result, and because of the tester, we need some calculations over here. So the calculation what we need like airflow calculation. So here airflow is the service value into power, the watts that we have the ceiling fan consuming, and the efficiency. How we calculate the efficiency? That is airflow divided by the power. That's it. So the next slide, if you go here you can see the air delivery. What we do is the section A, section A prime, section B, section B is just a x-axis to y-axis, z-axis, and z prime axis like that. So each value there is a nanometer we set, and here is the distance. You can see 40 mm to 1000 up to 1000 mm, but we calculated 760 mm. So here the air delivery, what we get 192.91 meter cube per minute. It's with the old blade design, and the new blade design we got it like 223.09. So here you can see the significant differences just because of the twisting angle and the new design shapes. So here is the overall, if we do the overall performance test like power consumption, current and speed overall, we can see the air delivery, we got 192.91 meter cube per minute. Here the service value is 3.0 meter cube per minute per watt, which is according to our South Asian standard is 3-star rating. But if we go to the new blade design, here we can see the service value we get 3.54, which is according to the 5-star rating. And the air service value we already how calculated we already discussed in previous slides. Also the if you see the sound level previous one is 64 decibel, but here is only 61 decibel. So which is far more better than previous designs. So here is the assembly flow chart here for the ceiling fan. So from starting from the starter grinding and the checking in gauge, then starting stator connection and checking series line. After that, the stator and the rotor auto color for the product trust, and the rotor pushing in the bottom cover. Uh, so far here you can see, then after that air gap check between the stator and rotor. After that body fixing part and with the screws we do it, then considering the clamp fixing, after the capacitor connection have been done, then the decorative, the border, if they have a decorative option, we can do the decorative some paint in the body. Then the motor loading on over at conveyor, we do it. Then it passes through the running in bus line, and then we do the high voltage check. Here the low voltage check have been done, the running voltage check, the speed, power, current check. So these are the main the in process QC what have been done. Any noise have been done. These are the checking for the in QC process. After the QC passed it, then we do the loading process. The blade and screw have been fixed up. Body polishing have been done. Then the if nameplate, then wrapping and accessories. After that, we delivered to store. So this flowchart provides a structural overview of the steps involved in the ceiling fans assembly, highlighting the attention of the details in the both the assembly and the quality assurance stages to ensure the final product that meets the required standard and specifications. So, so these are the main QC tests that we have been done to check the quality, because after manufacturing, these are the highlights. Without QC, we can't go for the market unless it will be a bad consumer review on the products. So what are the tests we have done here? You can see the high voltage check, insulation resistance, leakage check, low voltage check, running voltage check, speed check, current check, humming noise check, frictional noise check, gearing noise check, imbalance check. So these are the check we have been done before sending to the delivery sections. And this is, you can see the ceiling fan. So from this board, my another group member, he will share you the slide. I am giving him the option. Yeah, you can share your slide.
It can be seen, right?
Wait, wait.
I already shared my screen. It can be seen, right? Anyone? No. Yeah.
Okay.
Not share screen share also.
No,
Actually.
Thank you, Fakir, for handing me over the project to for the description. So, in this part, we will speak about the parts of our project. So, this is the bottom canopy, and the next is the top canopy. Then there's the rod, down rod for shaft assembly, and finally there's the cover of the casting. And you can also see the rivet for the blades parts. That's only the common design for the rivets. We used like 8 to 10 rivets for our projects. After that, this is the die casting rotor, and next is loop binding nylon clamp, and finally blade damping washer. So if I say that in detail, so now we are going to share how we designed our modified shape in Fusion 360. So we actually modified the fan blade. Initially, it was symmetry in both sides. That means the both side angle was similar. But after that, we have made that one angle is 9 degree and the other angle is 5 degree. So if you see that it's an aerodynamic shape, the thicker part is 5 degree from the middle and the other part is 9 degree from the middle. That's the innovation. I'm just going to demonstrate how we designed it in the Fusion 360. So that's how we just made our design and made a modified design. This is different from the existing design. And for the modified design, we got benefits from many factors like extended RPM, extended airflow, less noise. So after making the design, I'm just going to show how we created the toolpath for the CNC machine. So this is the toolpath we created by the Fusion 360. And for creating the toolpath, we initially just fixed the setup. I mean the alignment. Then we created the adaptive clearing, then the pocket clearing, contour clearing, and finally 2D pocket clearing. So it took almost an hour for creating the toolpaths. And after the finishing of the simulation, we just went to the actions and post-processed. Then we just created our G codes. I'm just also going to show the G codes here. So this is the G codes of our modified design. And it took just a minute to create it once we are done with the simulation. And that's how we just modified our design from the existing design and got better results. And finally, we created the G codes for the CNC machines. Now I'm just going to hand over to finish and for the rest of the descriptions for our projects to Sabab Al Farabi.
Thanks, Momen Shahriar, for giving me the opportunity to explain my portion. Hello, this is Sabab Al Farabi. Here is my part. Potential future research directions. We just sorted out in some major points. Firstly, automation in assembly process. Researching advanced robotics and automation for precision and efficiency in assembly process aims to reduce human error and speed up production. Then sustainability practices. In future research in sustainable manufacturing for ceiling fans could focus on using recycled materials, eco-friendly coatings, and assessing the product's life cycle environmental impact to appeal to eco-conscious consumers. After that, advanced materials. Exploring new materials for better fan performance and energy efficiency, including those that reduce noise or improve airflow, is a promising area for research. And lastly, smart fan technologies. Researching smart ceiling fans with IoT integration for app control, energy tracking, environmental adjustments, and maintenance notifications can offer significant benefits. So, by focusing on these areas, the ceiling fan industry could continue to innovate and improve both the efficiency of production process and the quality and functionality of the of the final product. At last, we can say that the detailed examination of the ceiling fan assembly process shows a structured and careful approach to manufacturing, ensuring high quality and safety standards. The process includes check at every stage, highlighting the manufacturer's commitment to reliability, aesthetic enhancement, protective treatments meet market demands for functionality and design appeal. These practices go beyond compliance, building a reputation for excellence and sustainability, embracing advanced technologies, sustainable materials, and consumer studies can revolutionize manufacturing. This commitment to improvement enhance efficiency, reduce environmental impact, and engage users, staying competitive in the home appliances market. That's all. Thanks a lot.
Thank you, everyone. Thank you, everyone. Thanks for the presentation. It's done. Thank you.
Thank you.